Hi, my name is Brice, and I'm a geologist in the mining industry. I aim to entertain people with knowledge about geology, the study that has to do with everything about rocks and minerals. Welcome to my channel, Rockology. First off, it's great to be back. It's been 11 months since I've uploaded a video, and the reason behind this is because I've been starting off my career in the mining industry after graduating college and of course finally finding a job. And as you can see, I've collected a copious amounts of new rocks from collecting, buying, trading with other rock collectors, and other methods. I'm now ready to get back on track and share more videos on geologic knowledge, and I'm glad to have you with me. As always, stay tuned for the end of the video and we'll show you the meme of the week.
Who's that? Geology meme.
Our subject today is physical, chemical, and optical properties of minerals. We now know what a mineral is, so we will now learn how to distinguish one mineral from another based off its properties. Properties are separated into two categories, hand samples and thin sections. We'll be only focusing on hand samples for now, and hopefully in the future I will be able to teach you about thin section properties. On top of this, I still have to teach you a few things so you would even be able to comprehend thin section properties. Now, properties allow us to differentiate between one mineral and another mineral. So if a mineral that we're looking at has one of these properties or doesn't have one of these properties, we then can exclude or include it in our group of minerals that we think it is based off these properties. And the more properties we include to test, the more minerals we can knock off our list of what we think the mineral we're looking at is. Now, before we start this video, you need to know what the difference is between a rock and a mineral. And we're going to use this fluorite piece as an example. This one crystal that's up front, right here, fluorite, is a mineral. But now, since it has all these other little minerals of fluorite all over the place on it, interconnected with it, and they all crystallize together, this is a rock. So mineral, 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 mineral. These are all minerals individually, but together, all together, since they crystallize together, this is a rock. And one other thing. Let's say that you send a geologist or someone who's well versed in rocks and minerals a picture of a cut gemstone or a rock in general or a mineral in general, and you ask them to identify it. This is going to be very hard because a picture can only tell you so much what rock or mineral you're looking at or what cut gemstone you're looking at. A cut gemstone pretty much loses any identifying characteristics because it's been cut. It doesn't have its crystal shape that it naturally came in. You're only going off of a color in that picture. You can guess it could be sapphire, it could be kyanite, it could be a diamond. You don't know because all those things can have the same color. So bear in mind that sending a picture of the rock, mineral, or gemstone in question that you want identified is not going to be a good way to figure out what the mineral is because there's no way to do these tests that I'm about to describe to you that could narrow down the suspects of what the mineral is. So when we pick up a mineral, what's one of the first things we should look at as a property? Well, the first thing we can look at is something that's known as crystal habit, which is a physical property. Now, crystal habit is a term referring to the shape of a singular crystal or a group of crystals. There is a long list of different names for crystal habits, and they themselves are separated into two groups. One for individual crystals and the other for crystal aggregates or groups of crystals, as I said earlier. Now, let's show you a few examples of these different crystal habits. The first is Botryoidal, meaning bunches of grape-like in shape. Dendritic, where it has an appearance similar to plant life or branches. Acicular, kind of like really elongated icicles or needles. Fibrous, the mineral has a fiber-like appearance and almost looks like hair. Prismatic, elongated crystals with identical faces parallel to a common direction. There are numerous others, and we will show them when it comes to identifying a mineral when we talk about that specific mineral and show its crystal habits. Next is looking at the overall perfection of a crystal, which is another physical property. Now, this is separated into three categories. The first is euhedral. A euhedral crystal will look exactly like what you would expect a crystal of that mineral to look like. A subhedral crystal looks kind of like what you would expect it to, but it's not perfect. Maybe it crystallized imperfectly, or maybe it's been bashed around a little bit, but it looks pretty much like what you'd expect it to. The last is anhedral, which means it looks nothing like what you would expect it to. And this can happen for several reasons. Of course, maybe it's been eroded, or it's been bashed around, or something happened to it that just caused it to not retain its crystalline shape that would be a identifying characteristic to tell it from one mineral from another. Now, the reason why this is important is a lot of minerals will form a lot of different shapes under different temperatures and pressures, and of course this means I can try to tell the difference between one mineral and another based off of its shape that it has. For instance, this fluorite decided to form crystal shapes that are square-like. In this garnet cluster here, all the garnets have formed a somewhat of an octahedron-like shape. So therefore, I can tell the difference between these two minerals based off of their different crystal shapes and how perfect those crystals formed. But also keep in mind, fluorite and garnet can form different shapes under different pressures and temperatures, and possibly different chemistry that may be inside the crystalline structure that could affect the shape that it wants to take to withstand those pressures and temperatures that it formed under. Now, I don't want to go too into context with this because I'll make your mind spin, but basically some minerals have the ability to form a lot of different shapes and appearances based off of the way they formed and the chemistry that's within them, and some minerals can't form as many shapes as other minerals can. Now, one that the public may loosely know about is known as the Mohs hardness scale, which was developed by Frederick Mohs in 1812. Now, the scale originally tests the amount of pressure that a mineral can go under without being abraded or scratched. Now, its original use was to scratch one mineral against another, testing what is known as relative hardness, because it's relative to another mineral's hardness. So basically, he would take all these different minerals and scratch them against each other and rate them, saying, okay, this one scratched this one, but this one didn't scratch this one, so this one is stronger than this one, but this one is weaker than this one, and this one is stronger than this one. And this is basically what he did. Now, the more scientific version of the Mohs hardness scale, thanks to modern technology, tests what is known as absolute hardness. And absolute hardness is a mineral's ability to withstand permanent deformation. Now, minerals will have a bit of a range of how hard they can be, and this is because of, again, the pressures and temperatures and the chemistry that they have within them that control their properties. So, for instance, garnets can have a range of hardness of, I believe, around like a 6 to an 8, which is kind of a large range on the Mohs hardness scale, but this is again due to how it formed and what chemistry that the garnet specifically has. Now, while the modern Mohs hardness scale absolute hardness test is done by a machine, relative hardness can be affected by a couple of variables. This is, of course, by how hard you could be pressing against another mineral with another mineral, and another thing that could affect it is the angle of which you're applying that pressure. And another thing we have to consider is impurities within a mineral's crystalline structure that could be affecting its true hardness. Now, for relative hardness, since I don't have a true absolute hardness scale test machine, I actually use a scratch toolkit test. Rather than scratching my minerals against another and, hurting them, all I have to do is take one of these and I can just scratch it and then look at it with a hand lens to see if it's scratched or not. Now, since the Mohs hardness scale goes from 1 to 10, there is actually another test that kind of takes advantage of hardness to test another physical property, and these are what's known as streak plates. Streak plates have a hardness of 7, so that means that any mineral that is above the hardness of 7 will not be scratched by these streak plates. Now, the point of a streak plate is to get a streak color. So if you take a mineral that has a hardness of 7 or less and scratch it against these black or white streak plates, and it will leave behind a color. The reason why we have black or white is because, a black streak won't show up on a black plate and a white streak won't show up on a white plate. So you have two of them in case you have that kind of issue. And anyway, so if you scratch a mineral against it, it's going to leave behind a color, and that color is an identifying characteristic. I remember in college, I was scratching this piece of hematite, and the color that came off on the streak plate was not what I was expecting, which was kind of interesting because I believe the hematite was either gray or red, and the streak was the opposite color of what I thought it was. It was either the hematite was red or gray, and the streak that it left was red or gray, but it was the opposite of what the mineral's color was. And just so you know, if you're interested in all these little tests, the streak plates, magnet, and the hardness testing tips are all in here. I think I bought this for like $150 off of Amazon if you're interested. Now, if you are successful in breaking a mineral and the area that you have broken crumbles away off the mineral, it is considered brittle in this section of physical properties known as tenacity. Tenacity refers to a mineral's toughness and its resistance to being deformed. So if it is easily deformed, it is of little tenacity. Besides brittle, it can be elastic, which is bendable, but it returns to its original shape. All minerals can be elastic, and this is actually a bit of a weird thing. So this is going to be a bit of a hypothetical, but bear with me. Imagine you had a cylinder of a singular mineral, so let's say fluorite, and this cylinder is X meters long and Y centimeters wide. Now, if I could cut down the center of that cylinder, not all the way, but say 3/4 of the way, then go back to the beginning of where I started cutting, I could probably pinch those two ends together where there is now a void from the cut and pinch them together and then let go, and they would return to their original shape. Now, that's not extremely elastic, since say the cut is only like maybe a centimeter wide, and I squeeze the centimeter space closed at the end and then let go, but that still is elasticity. The rock is still elastic, it's just not as elastic as a rubber band. Another is being malleable. Malleable is when it can be hammered into shapes. This is a very good example of like sheet gold. Sheet gold and also aluminum are things that can obviously be very malleable. Ductile is another one where it can be drawn into a wire-like shape. A very famous one is, of course, copper, which we use in a lot of wires. And another is being sectile, which is capable of being cut into shavings with a knife. And a good example of this is like aluminum or gold. Now, if you were successful in making a mineral break, you should look at the pattern that's left behind on the mineral, which is a fracture pattern. And fracture is another physical property. There are 6 major kinds of fractures. The first is even, which means it's smooth, planar surfaces, and a mineral example is halite. Uneven, which is where it has rough, irregular surfaces, and a mineral that has rough, irregular surfaces is rhodonite. Hackly is jagged fractures with sharp edges. A good example is copper. Splintery, where it forms sharp splinters, and a good example is pectolite. Fibrous, forming fibrous material, and a good mineral example would be chrysotile. The last is conchoidal fractures, which is breaking with curved surfaces, kind of like glass does when you break it. And a good mineral example of this would be quartz. A lot of crystalline atomic structures and chemical bonds are not the same in all directions. So when you try to break a mineral, most minerals are going to break along a preferred surface. So it will break, or what we like to call cleave, along a preferred direction. Now, this brings us to our next physical property, which is known as cleavage. Now, I know what you're thinking, and no, I'm not talking about that kind of cleavage. Listen, we all like that kind of cleavage, and geologists love cleavage planes, but we're talking about geologic mineral cleavage planes. Get your mind out of the gutter. I trust me, I know. I went through the same thing when I was a sophomore in mineralogy. I giggled when I heard cleavage. Now, when you break a mineral apart, if the surfaces that are left behind are planar and smooth, it is said to have good cleavage. And cleavage is when you break a mineral and that area that's broke parallel to a plane of atoms. Now, an exception to cleavage is anything that breaks in conchoidal fractures, and that's because conchoidal fractures breaks in curved surfaces, which is not breaking parallel to a plane of atoms. A majority of minerals have cleavage. The first is basal, which means it has one plane of cleavage. The second is prismatic, where it has two planes of cleavage at 90 degrees to one another. The next is non-prismatic, where it has two planes of cleavage, but they are not at 90 degrees to one another. Cubic, where it has three planes of cleavage at 90 degrees to one another. Rhombohedral, where it has three planes of cleavages, but they are not at 90 degrees to one another. Octahedral cleavage, which has four planes of cleavages. And dodecahedral cleavage, which has six planes of cleavage. Now, the one thing that could be possibly confused with cleavage is something that we know as twinning. See, when you have a mineral that twins, so two crystals growing in two opposite directions, but they're growing through one another, and say one breaks off and you have the surface right here from where it broke off, this may confuse you after that part breaks off because it will show something that's called parting, which looks similar to cleavage. Now, a common physical property is one that's very well known with physics, and that is density. Now, how we tell density of a mineral is if the mineral is big enough, we will cut it into a cubic shape. And this cube is going to be 1 centimeter cubed. So basically, the sides of every square of the cube are going to be 1 centimeter. This then allows us to measure the mineral in grams per centimeters cubed. Then if we take the density of that mineral and we divide it by the density of water, we then get what's known as specific gravity, which is another physical property. The higher the density, the higher the specific gravity will be.